All right. So, hello and welcome to this next lecture in the ongoing series of lectures in digital prepress. If I remember correctly, we had completed our discussion on the various parameters and various other terminologies, ending with our discussion on a very important topic that was gamma. So it was a mathematically speaking, it was a relationship between the brightness that is coming out of the screen with the level. Level means the pixel intensity of the particular pixel. So that was what gamma was, and uh, we also not only saw the mathematical experiment, but we tried to kind of analyze the physical impact or the source, uh, why gamma encoding is actually required, why gamma correction is required, etc., for the images. And we also saw what impact it has, changing the gamma values, lowering it, uh, what impact it has on the image. We also saw the different types of gammas, right? Image gamma, display gamma, system gamma. So, and all those things we discussed. Now today we are going to begin our uh, another kind of a long journey. I mean, not long really, but at least this would take maybe uh, 2 or 3 lectures minimum. Uh, but it's nothing. I'm not saying this to create fear in your minds, but this is a very important topic. And most of the time, what we see that we simply discuss. Okay, this is center to center dot distance is same, so it is. This is known as aim, uh, and when it varies, that is FM. That is our entire knowledge on screening. But I tend to discuss and teach a little bit in depth, or impart a little bit in depth knowledge in the digital screening technique, starting with this particular lecture. From here on, I will start this. Why I told that this is a journey, because today's lecture marks the beginning of our ultimate goal. What is the ultimate goal of prepress? To create dots on a plate, right? So at least for offset, right? So that is the end. You can say that is our end goal. So whatever we discussed till now were kind of the fundamentals, kind of the terminologies. But from today on, we will actually see how dots are created, how dots are generated, and ultimately they are created on the plate. Okay, so this is going to be a very interesting, uh, series of lectures. I hope you would enjoy it. I hope you would like it. So let us begin. Now see the image in front of you that I have given in front of you. So start with the left one. Now here, now just try to think what this might represent. Okay, what this particular image might represent. This is image 1, 2, 3. Okay, what might this image represent to you? Just pause the video here for a minute and try to think about it. What this is representing. Uh, I will give you the answer myself, but try to think about it for a second. What it is representing. See, this is a series of pixels. Okay. If you remember earlier, I told you that there are three terminologies or three units using which we can measure resolution, didn't I? That is, one is LPI. We are familiar with LPI. Now, why? Number of lines in a screen, in a contact screen. This so that part we are completely clear about, and we have seen a contact screen in our lab, so that is clear. PPI also we have very good idea, because we are all using these digital screens, digital displays, and all the digital displays are made out of a series of pixels. So that also we have very good idea, the pixel per inch. Now we are coming to the topic of DPI, dot per inch. There is a relationship between PPI and DPI. What is our goal here? Try to think of, forget these images for a minute. Just try to think about this. Then what is our goal here? We are seeing a digital image on a screen, I mean on a digital display, right? and ultimately we need to convert it, or we need to discretize it into a series of dots, physical half-tone dots on a aluminum plate. Is it not? That is our aim, that is our goal in the entire prepress operation, to create those dots. So from that perspective, or from that point of view, we are starting these individual boxes. They're all pixels, and this is a grid of 14 by 14 pixels, right? 14 rows, 14 columns, right? 14 by 14 pixels. Now, along with this, or using this 14 by 14 grid of pixels, we are creating one dot. Okay, so try to imagine it like this. So let us say there is, you divide your entire image, into a series of 14 by 14 pixels, or 14 by 14 grids, right? Let us say your entire digital image has been divided into 10 such 14 by 14 pixels. Okay, and each of those 14 by 14 pixels is representing one dot. Now, how those dots are created, uh, what is the mathematics behind it, we will come to that later on. But I am giving you the very brief overview about the relationship between pixels and dots. Okay, now here, as you can see in front of you, that this is a 14 by 14 grid of pixels. So this has a certain pixel intensity value. All these pixels have a certain intensity value. Let us say if it is a, now try to correlate this. Let us say all these 14 by 14 pixel in this vicinity, or in this area, they are all having very high pixel intensity value. So that means it is a kind of a highlight area. So that should be and beside that grid of 14 by 14, there is another 14 by 14 pixel grid, which is maybe having very low pixel intensity value. All those pixels. That means it's a shadow area. So in terms of dot size, this 14 by 14 grid will be represented by one dot, and the other 14 by 14 grid which is beside it will also be represented by another dot. But the question is, what is the size of the dot? Whose dot size will be higher? Of course, the shadow area will be represented by a greater amount of larger size dot in comparison to this highlight area. So this is how pixel intensities are translated into dots of varying sizes. Okay, so that is what is shown over here. Basically, the screen cell is kind of, you can say that the building units of a digital dot. Okay, screen cell that is written over here, this is nothing but a pixel only. So that is, this multiple pixels come together to create. Now I will give you the overview when we talk about ripping and all, but let us try to understand how this actually occurs. Okay, so my entire image or entire, here now we are talking about our idea about digital images are now clear. Now we are talking about the CTP, which is basically creating the plate. Now your entire plate, let us say, have been divided into this series of all these screen cells, right? All these grids. Now the CTP is capable of applying laser on specific areas and burning those areas. Burning means exposing those areas. As soon as certain areas in the plate will be exposed by the laser in the CTP, that area in the plate will get exposed and will ultimately get developed, creating the exposed area basically, or image area. Now, if the CTP, we send information to the CTP, or the CTP itself is capable of burning certain areas, now what will happen? CTP will burn certain areas within the certain blocks or certain screen cells to expose that area, and ultimately such a area will be created, which is the halftone dot. So let me draw this, if I get the opportunity. So let me just give me a moment. I will try to draw this. So I'll try to draw what I am saying. Okay, so let us say that you have this image. Okay, you have this image which you are trying to, you know, discretize and print with the help of a plate. So you need to develop, I mean, you need to create that plate. Normally, how do you create a plate in your conventional method? You simply apply the coating on the plate, let it dry, and then put the negative or positive depending upon what plate you are preparing, and then expose it through a light. Okay, with the help of a light, and thus the plate is created, and the film itself with which you are exposing, that is discretized, that has halftone dots. So the plate automatically will also have halftone dots. But CTPs, what they do, they divide your entire image into, or the entire plate into a grid like this. Now, what is the resolution of this grid and all this, that we'll talk later on. Okay, so like this they divide your entire image on. Okay, now what will happen is, let us say this chunk of block, so entire image is divided into all these screen cells, right? Now this chunk of, or this grid of screen cells together will be considered as a conglomerate, or will be considered as a unit of what? Unit of a dot. So let us say that this is a highlight area. If this is a highlight area, then naturally there will be some algorithms which will work to determine. I will show you how those things work, but I'm just giving you a brief overview. So those certain areas or certain screen cells will be burnt off by the CTP. This grid is not real. This is an imaginary grid. Based on this, the CTP will expose the plate in only certain areas. So it may so happen that this block or this area in the plate is exposed by the CTP. This area is exposed. So this area is exposed. So that means what? That this entire chunk of, or the entire grid of screen cells is represented by this dot. Now you will ask that this is a square dot. Yes, those things will come later on. But for a minute here, consider this, that this entire grid of screen cells is represented by the single dot. Now, beside this, there is another such grid, right? This is a, let us say this is entire block of pixels is having a average pixel intensity value of 200, let us say. That means it is a highlight area, but this grid of screen cells or pixels is having a, you can say, this uh, pixel intensity value of 102. Then that means this is a relatively darker area than this one. So larger number of areas will be exposed while for representing this particular chunk of pixels. Why? Because this is representing what? This is representing a shadow area, or I mean a darker area. That means the size of the overall dot here will be increased in comparison to this area. So the dot size here is small, dot size here is larger. So this is how normally a CTP works. Okay, or the dots are created. Digital dots are created basically. Okay, so that is what is represented by this black area is nothing but the exposed area which will be exposed by the CTP on the plate, and this conglomeration of all this area will together create a particular dot. This is known as the digital halftoning technique. Okay, so that means, again I am repeating the very basic concept here. So your entire image, let us say this has a few thousands or few millions of pixels. Okay, the entire image is made out of few millions of pixels. So the CTP will also subdivide your plate into those many number of, or somewhat similar number of grids. So it will divide the entire plate into some grid like formation, and it will determine which area or which screen cell to burn off meaning to expose, right? And depending upon the pixel intensity values and what should be the size of dots, and this is determined by the RIP engine itself, so we'll talk about it later on. Depending on all those factors, it will burn off certain areas, such that areas which are highlight will be in those particular areas, smaller dots will be created. Areas that are shadow or midtone, larger dots will be created. So this is how CTP burns the plate to create the digital dot. Now the question is here. So this is, you can say that okay, so but one thing is has to be very much clear here, that what should be the size of this grid. That means here it is written in this context, or in this example it is written a size of 14 by 14 pixels together is uh, clumped up or considered as a unit for which one dot is created, right? This entire clump of, or entire grid of pixel is creating one dot, right? Now you can say that, is it always 14 by 14 pixel? No, it is not. So which is the determining factor, that how many pixels should I consider in a grid to create that dot? It depends upon your addressable resolution. What is addressable resolution? The output resolution of your CTP. Let us say your CTP, you are working with a CTP of 2400 dpi. That means your CTP is capable of producing, let us say that this is basically 1 inch, okay, 1 inch distance. Within this 1 inch, your CTP, if your CTP's addressable resolution is 2400 dpi, that means your CTP within this 1 inch distance of the plate can create 2400 dots, okay, 2400 halftone dots. This is what addressable resolution is. So you can imagine. Now consider this. Now consider this. This is one CTP having addressable resolution of 2400 dpi. Now there is another CTP which is having a resolution of, let us say, 12,000 dpi, right? That means for the same distance, for the same 1 inch distance, that CTP, this second CTP, can create much more number of dots in comparison to the first CTP, right? So automatically this entails what? That the number of pixels, this conglomeration of pixels that is considered to create a single dot by the second CTP is less in comparison to the first CTP. Try to wrap your head around this concept. Okay, say this is the one which is, this is the CTP which is working on the principle of 2400 dpi, or this is the addressable resolution 24. And in case of your 12,000 dpi, what will happen? What is going to happen? Now number of, this pixels, they will remain the same for the same image, but what is going to happen now in this 12,000 dpi system? Let us say that initially they were considering, in this particular example, they were considering how many? 1, 2, 3, 4, 5. Let us say 5. 5 by 5, that means 25 pixels. Just for example purpose, I am telling you, this mathematically these values won't match. So just for example, I am asking you to consider. Here 5 by 5 pixel chunks were considered for creating a single dot. So for 12,000 dpi, do you think the number of this grid, or number of pixels within that grid, will increase or decrease? Of course it will decrease. Why? Because in this case here you consider that 14 by 14 pixels are considered, together clumped up to create a single dot. But if your CTP's addressable resolution is high, then that means what? That means that lesser number of pixel grid will be considered to create a dot. That means ultimately total number of dots, so instead of 14 by 14, let us say a 7 by 7 grid of dot will be considered, pixel will be considered for creating a single dot. That means for a low resolution CTP, 14 by 14 pixel is creating one dot. But for a high resolution CTP, then it is possible that same 14 by 14 grid of pixel, if broken down into 7 by 7, then the higher resolution CTP will create two dots for the same area, isn't it? So that means what? That means if your CTP's resolution is increasing, okay, if your CTP's addressable resolution is higher, then the same area will be divided into greater number of these screen cells, is it not? Here we had got a chunk of 14 by 14 pixels, right? For that 14 by 14 pixel, we got one dot. But if we have a higher addressable resolution CTP, then naturally the number of pixels that will be, or pixel conglomeration that will lead to the formation of dot, that will lower down. So instead of 14 by 14, maybe that can be reduced to 7 by 7 pixels. So 7, we are, if you're using a CTP having a higher resolution, then for each of those 7 by 7 pixel grid you are getting one dot. That means for this and another 7 by 7 dot you are getting another dot. So for ultimately what you are seeing, is that your entire this entire pixel grid is, when they are broken down, the number of dot increases. That means when the CTP has got a higher resolution. Now how the CTP can have higher resolution, I will explain that also later on. But ultimately listen to this, that when your CTP has got a higher addressable resolution, then the number of pixels, or what is referred to as here screen cells, that will basically increase. That means the conglomeration of this pixel number, that will decrease. So for the same area, greater number of dots will be created, is it not? Because here you see that for the same 1 inch length, this CTP was able to create 2400 DPI, 2400 dots, and this CTP is able to create 12,000 dots for the same length. That means it is natural that the number of pixel conglomerates that will be required, or that will be required to create dots when your resolution is higher, will be less. That means your 14 by 14 pixels will go down to, let us say, 7 by 7. That means more than one dot will be created using the same space. So that is what the relationship between the CTP's addressable resolution and the number of dots that are created. Okay, so this is how dots are basically created in digital halftoning. Now the question is, another very vital question that I wanted to kind of address here, is that what is the fundamental concept here related to color halftoning. I will show you all that mathematical aspect, but just before we go into that mathematical aspect, let us consider what is the overall concept here. So first, one concept we were able to clear up, that is what is, or how this your digital halftoning is basically done, right? Now the problem was for digital halftoning is, if you are using a this type of dots, that means this dot has got no screen angle, that is here the screen angle is 0 degree, right? So here you don't have any problem, right? But the problem begins as soon as you start rotating your screen. Now why rotation is required in a multicolor printing operation of the screen? You know that very well, to avoid moire patterns. Now in order to avoid moire patterns, you need to rotate the screen angles of your multicolor or different plates. It was easy for us to do in conventional method, but it is quite difficult to achieve the same result with your digital halftoning. Now, why do I say that it is difficult? Now, see, as soon as you see, this was your screen cell, this gray area, entire gray area of 14 by 14 pixel was your screen cell. So this was fine. Now, what you need to do is, you need to rotate the entire, in order to rotate the screen, you need to rotate this entire screen cell as well. Now, if you rotate the screen cell, you are getting this jagged appearance, right? You are getting this jagged appearance. So what is going to happen? You cannot expect that these pixels which are on the outline, they will be partially lit. You cannot expect that only half of this area is lit. No, that is not possible. Pixel will either be completely lit up, or it will be completely switched off. Okay, so you cannot partially light up. Now the problem with this type of an idea is that as soon as you start to rotate this type of screen. Now this has been rotated by 45 degree, as you can see. Now if you start rotating the screen like this to a degree of 40, to 45 degree or etc., there is a problem. There will be a basic problem. So what problem will that be? You see, the width of the screen cell, that is going to change, and where you see in this particular case, that WR will be greater than WL. That means this size width of the screen cell and this side width of the screen cell, opposite side width of the screen cell, they will actually be different. Can you see why it is different? In this context, the size of the or width of the screen cell is how many pixels? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pixel width is this one, right? But on this particular end, you also ultimately you are this, because of the presence of this particular pixel which is lit up, the total number of pixel is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 number of pixels, right? So ultimately what you see is that the width of the pixel or the width of the screen cell at one end is higher than the other one. Now this is a problem. Let us, in order to understand or in order to solve this, let us just go back to the idea where it all started. Here you see, for each of the rotation of the screen cell, the corners of these screen cells must engage with the pixel boundary. This means what? This means that only acceptable angles are the one for which the corners of the rotated screen cell keep both a vertical and horizontal integral pixel distance to the lower left cell. Now, this is only possible under certain scenarios. This means, let me again explain what all this, uh, whatever I told it means. This means what? That the corner of the this screen cell must contain a minimum of one horizontal and one vertical pixel. That is how a corner is defined. Here, how is a corner defined? In this screen cell, one vertical side, one horizontal side. But here is, let me just clear this out so that you can see it. But here, as you can see in this corner, both these, the entire corner is made out of 2 pixels where the entire thing is vertical. There is no horizontal pixel at all. So this, in order to avoid this problem, you simply cannot rotate these screen cells in any angle that you want. You need to rotate it in a specific way such that the overall angle is overall pixel side is such that it contains a minimum of one vertical and one horizontal pixel at the corners. This is possible when you rotate the screen in this particular way, that is one step right and 3 step up, right? This is one step right means if you consider any of this, let us say if you consider this one, this particular line, okay? So how has this line been rotated? This length, this entire length is one step right, that is one step right, and this entire length is how much? This entire length is 3 step or 3 step up or 3 step down, whatever. Now if this is how the screen is rotated, only then you are getting a pixel or you are getting a screen cell with minimum of one vertical and one horizontal side, right? So ultimately, how to calculate the screen distance, how to calculate the screen angle if this is how you rotate the screen? The method of calculating is simply find out the tangent to it. What will be the tangent to this? If you calculate this, what should be the gradient? Gradient is tan theta will be equal to 1 by 3, and if you rotate it, this has been rotated in this way, acute angle. You rotate it in the other way as well, you rotate it in the obtuse angle way, then what will be the value? Tan theta will become theta 2, let us say theta 1 and theta 2, that will become 3 by 1 or 3 ultimately. So what will be the value of theta 1? Arctan of 1 by 3, and theta 2 will be what? Arctan of 3. So this will, I think, come about as roughly 18.4, and this I think will be your, let me just go and calculate this. This will be, yeah, so this will be so this will be arctan of 3, 71.6 degrees, right? And your other angles will remain 0 degree or 90 degree and 45 degree. This will remain the same, no problem with this. Now this means what? We did all the maths and all, that is fine, but this actually means what? it means that you simply cannot change the angle in any way possible for digital half toning techniques. If you wanted to change it to 15 degree, if you wanted a screen angle of 15 degree, that is not possible. Why that is not possible? This type of problems will occur, right? That where one side of the screen cell will be greater or will be lower than the other side of the screen cell. Or if you had used 75 degree, rotated the screen by 75 degree, then also what will happen? The uh, width of the screen cell in one end will be lower or greater than the other end. So this type of screen cells will not be possible. In order to get a screen cell or in order to get a dot, screen cell and dot I will use analogously, because one screen cell here is resulting into the formation of one dot. Screen cell means what? Screen cell means a conglomeration of dots, a conglomeration of pixels. So here a screen cell was used, 14 by 14 size screen cell. That means 14 pixels, a grid of 14 rows and 14 columns of pixels together is creating one dot. As I told you earlier, that this screen cell size will vary. Why? How it will vary? It will depend upon the resolution of your CTP. If your resolution of CTP is very high, then this screen cell size will reduce. That means in the same area of this screen cell, you can create more than one dot if your resolution of the CTP is higher. If you break down this entire chunk of 14 by 14 pixel into four components, right? If you in your CTP, your resolution is supporting creation of dots, or your resolution of the CTP is high, to put it simply, then it is possible to break down this entire screen cell into four components or four screen cells. One single screen cell can be broken down into four screen cells, and as a result of which four dots can be created instead of one in this particular in comparison to this particular example, right? So that is what a screen cell is. That is simply conglomeration of multiple pixels which is resulting into the formation of a dot in the CTP. Okay. Now, why the question here is why it is not possible to get a screen cell of 15 degree or a screen angle of 15 degree or 75 degree when you are using this type of a digital screening technique. Why it is not possible? Because you see, if you go to, I will show you in the later example what happens if you get a screen angle of 75 or 15 degrees. Ultimately, the problem here is that in order to kind of preserve the shape of the dot, in order to preserve the shape of, see, this is looking like kind of a round dot. If you look it from a little bit distance, it is looking like a kind of a round shaped dot. In order to preserve this shape of the dot, it is necessary for us to change the or rotate the screen cell or rotate the screen angle in such a way that the shape of this round dot is preserved. That is why we are in this type of a screening, digital half-toning screening technique, we are maintaining or we are preserving the shape of the dot, which is round in this case, at the cost of the screen angle. So this type of screening is known as rational tangent screening. I made a mistake. I think this is not rotational. This is not, I wrote it as rotational. It is not rotational. It's actually rational. So let me just rectify this. This is rational tangent screening. Now the question is why rational and why tangent? These two terms you have to understand very well. The reason it is known as rational, why? Because first of all, let us understand why it is known as tangent. How did I find out this? What will be the screen angle here? I took out the tangent value of the of this particular curve. I calculated the tangent of this particular curve to calculate the screen angle. That is why it is known as tangent screening. And why rational? Because this can be expressed as a ratio of two natural numbers. How? This was expressed as arctan of 1 by 3 and arctan of 3 by 1. So this can be expressed, this screen angle can be expressed by a ratio of two natural numbers. That is why it is known as, so that is what rational numbers are. If it is if it can be expressed by a ratio of two natural numbers or two integers, that is what, that is why this type of screening technique is known as rational tangent screening. Okay, so hopefully this part is clear. Now let us go to the next type of screening, which is, okay, here, so here as you can see the and screen angles are given. So for the same, it remains 0 or 90 degree remains. This is written as 0. This should have been written as 0 or 90 degrees. The other angle, it is actually uh, 18.4 degree, which we calculated later. This is 45 degree, and this is 71.6 degree. You can say that why this the greater angle is 18.4 degree, why this is 71.6 degree. They have taken from this angle. This is what the 0 was, and this is what 90 was. That is why it is. So naturally, this becomes greater angle, and this becomes a smaller angle. That is what. Now, so the thing is, how is this different from your conventional screening? In your conventional screening, this was placed at 15 degree, this was placed at 75 degree. So that has changed. So that has changed. Why? Because we are considering preserving the shape of the dot. Now, why I am saying we are considering preserving the shape, and how dot shape has been preserved by using of this particular angle, that will become clear when we go to irrational screening. There is, since there is rational screening, there is also another irrational screening. So there I will explain what I mean by when I say that dot shape is basically preserved. Okay, so hopefully this is clear. Now let us go to another concept, which is known as the supercell technique. Okay, so what is the supercell? Now here, as you can see, that the larger screen cells offer more accurate compliance with the angle, but they are undesirable since they are able to create various structures which are visible quite clearly. Because the more larger your dot size becomes, or your cell size becomes, it is more the possibility of that being detected by your eye that increases, and ultimately that will cause a loss of this resolution. Now, therefore, this new technique was created, which is known as the supercell. What it does is, it does not really magnify the cells, but they clump up multiple cells together. So, as if you take a look here, if you take a look over here, see, in this particular context, this has also been rotated 3 cells right and 1 cell down. This is how rotation has been done. So let me just draw it out. So this is one particular screen cell, that means this is one dot, this is one dot, right? This is another dot, right? So, and these are the other 2 dots. So that means what? Individually, we were using initially one screen cell, one set of screen cell. Acha, can you tell me what these numbers mean? 244, 255, 233, 206, 130. What does it? What does this number mean? These numbers are your pixel intensities. So your entire this is the overall digital image. Let us say that this is your entire digital image. Okay, this is your entire, for a just example I'm telling you, this is your entire digital image. Okay, now your screen cell you can say is a subset of your entire digital image. If your entire digital image is of the size 1000 and 1000 pixels along the width, and 1000 2000 pixel along the length, then that these many number of pixels are there in your digital image. And now if you consider small clumps of those pixels, let us say if you consider 10 by 10 uh, pixels, and if you break down the entire digital image into those clumps of 10 by 10 pixels, as I showed you earlier also, that 10 by 10 pixel grid is known as your screen cell. Hopefully this much is clear from the previous uh, thing. Right now, as you can see, that as I told you, so naturally these small boxes are what? These small boxes are your pixels, and the area which I have demarcated with red color, each of this is known as a screen cell. Okay, and this individual small box, this box, is a pixel. So naturally your screen cell is a subset of your pixel, or your entire digital image, right? And this screen cell is also responsible, you can say, for the creation of a dot. That means one screen cell equals one dot. Okay, hopefully this much is clear to you, how the kind of half toning is actually done. Now this concept of supercell is very interesting. See, uh, why this happens, or why it was needed at all in the first place to create this supercell. Supercell technique is nothing but clumping up multiple screen cells together. Previously, what was the screen cell? There were these individual types of screen cells available, right? Sorry. So now in this context, you are clumping up multiple screen cells together. Okay. What does it mean? That means this will lead to one dot like this will lead to another dot like this may be a small dot, this may be another big dot. So ultimately, what is happening? You are getting a particular area which is having your multiple dots. Okay, so ultimately the advantage of this is that individual cells can have different sizes and shapes. These differences are compensated for within the supercell, and together supercell screening keeps to the required screen angle. That is how the screen cell actually works. Now you see that the overall formation of dots in this screen cell results in what? It will not cause any loss of detail, because you are getting these dots, individual dots, but you are clumping those screen cells together. But there is another problem with this supercell technology also. Why is that? Now here you see, you get, this is your individual screen cell, right? And together they are making up a clump of 3 by 3 screen cells. As I told you, that depending upon the overall pixel intensity, there these dot sizes will vary. Maybe this is how the dot patterns are appearing. Now this increases the level of complication, or this increases the computation need of computational power to create the dots. Initially, what was there? Initially, the individual screen cells were there, they were not clumped together, and the dots were calculated depending upon the pixel intensity values, whether it is a a kind of a highlight value, highlight area, then a small dot, and if it's a shadow area, then larger dot. That was calculated. But here another layer of complication is added. You see, in this case, the RIP not only has to figure out what will be the size of the individual dots within the screen cell, but it also has to find out for all the cells, or all the cells within that supercell structure. So this is another kind of a problem which the uh, you know supercell technology provides. But there are certain types of screening techniques which can actually solve this problem by outsourcing this computational requirement to another hardware or another computational device, while the RIP just determines the shape of the dot within the screen cell itself. Okay, so this is what the supercell technology is. Now now you see, now we are slowly and steadily coming to the concept of irrational screening. Here you see, so this is your analog screening, no issues, smooth dots through contact screen or non-contact screen at 15-degree angle, no issues. But when you come to rational screening, what do you get? You get, in order to preserve the shape of the dot such that it appears roundish itself, we move, or we turn the screen in such a way, we rotate the screen in such a way such that the shape of the dot is preserved. So when can this shape be preserved? Only when it was experimentally found out that only when we move it one step left and 3 step up, or one step right, 3 step down. This is just analogous. One is 18.4, another is 71.6. So ultimately, one step left, 3 step up. When this rule is being followed, only then, and the screen is rotated using that rule, only then you can see the overall half-tone dot that is being created, the shape is being preserved. Now, and this is known as the rational tangent screening. But what if I am required to maintain the uh, screening screening angle? Then this irrational screening comes into effect. See, the main difference with this rational and irrational screening, this lies in the mathematical difference between this rational and irrational uh, numbers. So if rational is what? Rational is any number which can be expressed as a fraction of two integers. But irrational is not. Numbers are not able, we are not able to express that number is a ratio of two integers. This basis of the irrational screening is a screen matrix on which the distance from one dot center to the next corresponds exactly to a specific value. So the distance from this point to this point, that is center to center dot distance, this corresponds to around 166.66 micrometers, or this is for a 60 LPI screen, or LPCM screen, I'm sorry. Now this irrational screening conforms to this perfect dot shape, perfect screen angles at the cost of the dot shape. That means what? Here you see the dot shape has been distorted. In case of your irrational screening, see the dot seems to have been distorted. It is appearing to be like a elliptical shape of a dot instead of a circular dot. Not always. In certain cases, it manages to maintain that one left and three up rule that may be maintained sometimes, but not always. So ultimately, what is happening? The dot shape is compromised, is changed at the cost of the screen angle. Right? Or conversely, you can say, stating conversely is better, that the screen angle is preserved at the cost of the dot shape. But in case of your rational screening, what is the fundamental there? That your dot shape is preserved at the cost of screen angle, right? Because your irrational screen cannot comply with that particular screen angle, which results in the formation of perfect round dots. That is why, because it is shaped in such a way, or the screens are rotated in such a way, that the dot shape gets changed, or dot shape gets distorted. This is the fundamental difference between rational and irrational screening. Hope this much is clear. So now, since we are, kind of okay with our concept of this, uh, what halftoning is, the basic fundamental concept of halftoning, and how your entire digital image is converted into a series of what is known as a screen cell, and those screen cells are responsible for creating your dots onto the plate, which is, I mean, the size of the dot will depend upon how your rip engine is basically converting your digital image to a you know first into a continuous tone and then into a bitmap kind of an image. Depending on those concepts, the dots will be created. Now in this part of the lecture, I will be talking about a little bit about the mathematical aspect of digital half-toning, how this can be done. So this may be, uh, I hope this will be clear to you, because I'll try to make it as simple as possible. So consider, if you remember in my earlier lecture somewhere, I told you any digital image is basically an image matrix, and hopefully you know why I said that. Because you see, uh, in the Photoshop example also, you got so many pixels. I think there were 1,29,600 pixels. So they may be arranged in certain way. Let us say that we are talking about a image which is having 20,000 pixels. Then it may be arranged in 200 length along the length and 100 along the width of the image. So this is how an image is made up. Now this is for a single channel. For the red channel, there will be a matrix. Image can be represented as a matrix. So matrix of what? So let us say that this is the red channel image matrix. So this will be a matrix where there will be, let us say, multiple, what should I say, multiple pixel intensity. So this may be 10, 250. So for this is a 8-bit image, obviously. So 250, 50. So like this it will go on, and if up to 200 n is 200 here, and along the row also, along the various rows also, there will be, this will go like up to 100 n. So that means we are talking about a 8-bit image which is in RGB mode. So this 8-bit image in RGB mode is composed of three matrices, where the dimension of each matrix is how much? 100 by 200, row into column, 100 by 200. Okay, so these three matrices are interlaced on each other, and when we switch on that particular layer, we are only able to see those intensities. So what are these values? 10, 250, 50. What is this value? This value is what? The pixel intensities. These are the pixel intensities, which we saw as known as levels in Photoshop. These are the pixel intensity. For PS, it is known as Photoshop levels, and this is ultimately the pixel intensity. Okay, so hopefully this concept is clear. Let me just clear this out. Okay, now let us say we have got one image. We are talking about a grayscale image, single channel image, for ease of understanding. Let us say we have got a image which is 4 by 4. Okay, one 4 by 4 image. This is a single channel 8-bit image, right? So what will be the, if this is your image where X is the row and Y is the column, then the value of this I, that is image, the values of this I will range from what to what? For an 8-bit image, it should be greater than equal to 0 but less than equal to how much? 255 for your 8-bit image, right? So let us say this is the values are like this, arranged like this: 250, 30, 70, 90, 100, 200. Okay, so let us make this 230. You will understand in the end why I made this intentionally high value. Okay, so fine, then let us say we are going here for 80. Here 20 I have not given, then here 30, then 50, then here how much? 15, and let us say 40, 60, 20 I have already given, no? Yeah, so 70 also given. Let us say 110 and 25. Okay, so this is what the image is. This is what the image is looking like. Huh? So this much hopefully is clear. So this, from here on, we will do something which is known as a important concept, which is known as thresholding. Now what we have to do is, the basic idea that we need to know about is something known as thresholding. So what is this thresholding concept? I will do something to my image where I will test that if the pixel intensity value is above a certain point or above a certain value, only then those pixels will light up. That I will do. So let us try to understand how this thresholding basically works. So this is, thresholding is nothing but actually another image, resultant of which, when we add that particular image, or we modify this original image with that thresholding function, then the resultant is binary. That means the resulting image will be if the pixel intensity is below a certain value, then it will be, those pixels will be 0, and if it is above a pixel intensity value, then it will be 1. That means what? Let us say, let us consider let us consider this fx, okay, which is basically the thresholding function. This is another constant, we call it as constant intensity block. Why? I will show you. Let us draw that block first. This is another 4 by 4 block. Let us add some values to this block. Let us say it is 50. This will depend upon what type of this thresholding you are doing and what is your nature of the image and all. Now, for my case, okay, so one thing let me do, let this be 200 itself, okay. Why? I will explain it later on. Now, for my case, what I am trying to do is, I am trying to threshold the image over 250. That means, my intention here is to turn on all the pixels which is above 250 after I add this constant intensity block to my original image. Now what you have to do is, you simply add this constant intensity block with your original image. So what will be the value? This will be 60, this will be 300, this will be 280, this will be how much? 120, this will be 140, this will be 250, this will be 250, and so on so forth, like that, okay. So ultimately you get all the values. Now my condition was what? That I will turn, the condition that I gave for thresholding was that I will turn on all the image, all the pixels which is having a pixel intensity value of greater than 250 after I add this block to my image. So now if I draw my image now, but not with the pixel intensity value, but just with which pixels are lighting up and which pixels are switched off. So what will be my output ultimately? Which pixels will be lighting up? Those pixels which are greater, okay, let me make this greater than equal to 250. So which pixels are lighting up? So I will try to shade those pixels, or better no, I will shade the remaining other pixels basically, so that it will show that those pixels are white, okay. So this is dark, this is dark, this is dark. Why these are all dark? Because this is only becoming 60. Is 60 greater than 250? No, that means it will remain switched off. Those pixels will remain switched off. This is dark, this is dark, this is also dark, this is dark, this is dark, this one, this one, this one, right? So that means what? I am getting a what you can say, I'm getting a pixel chunk, that is this 2 by 2 pixels, this area is lighting up. Ultimately you see that this is how a dot is being created. Why am I saying this? This itself is the screen cell, as we discussed earlier, a conglomeration of pixels together which is responsible for creating a dot. And how, which pixel to which pixel is lighting up and which pixel is not lighting up, how to determine that? That means which pixel will ultimately, which area will ultimately get burnt or exposed by the CTP, how to determine that? Through this method, through this particular method, okay. So this will be the dot size. All right, this will be the dot size, right? This will be one dot that will be formed. Now we come to the important point. Now we have to determine this simple mathematics is over. Now we have to determine what? That how to determine or how to find out what will be the dot size, or that means how many pixels will light up or how many areas will be burnt by the CTP. All this meaning is same. If, or depending upon which area is shadow, which area is highlight, which area is that, right? Now consider this. What is my threshold? Let this constant intensity block be same, okay? Now consider this example, that I have considered a threshold value of, I have considered a threshold value of 250 and up, right? 250 means what? 250 is it 250 pixel intensity? 250 means pixel intensity value, right? I am saying that if any pixel after this operation of thresholding has a pixel intensity value greater than equal to 250, though only those pixels will light up. Rest all pixels will remain switched off. That means those areas in the CTP will get burnt off. laser will be exposing those areas, right? So that will be the dot size overall using this screen cell. That is what I wanted to tell. Now the question is or how to determine this particular thresholding value. This is an interesting question and an important one, that how to determine the thresholding value. And why did I, in this context, I just give you an example of 250, but this is not random at all. This has to be very carefully determined. Now, why am I saying that this thresholding value is important? Can you think of it? Can you tell me the reason why I am saying this thresholding value is important? Pause the video here for a minute and think. See, this ultimately I will show you how this thresholding value will determine what is the size of the dot you are getting. How you might say. Okay. Now let us consider this. So I'll have to do some calculation myself and then consider or set that thresholding value. See, if I set the new threshold value as 120, okay, this is what the threshold value, new threshold value I am considering. Okay, now consider this. Constant intensity block remains the same, that is 50. And how to determine this, that also depends upon what image you are considering basically. Okay, so those are other considerations, but let us consider this first factor. Threshold value is 120. Now if I draw this new image after thresholding and after adding the this constant intensity block to the original image, what will be the ultimate result or ultimate output? That means what will be the which pixels will be lighting up and which pixels will be switched off. Ultimately, what will be the nature of the dot that is created by this particular sequence? Now, for that, I need to make one modification. I think. Which modification do I need to make it a more kind of uh, nicer kind of an image? A nicer kind of this thing. Okay, so what I will do is I will make this as 10. Okay, this one as 10, and okay, fine, this only this much is enough, right? Now result is same. That means when you add only after this only this modification I have made, this is just for cosmetic change. No, I will explain, you will also know why I am making this change from 110 to 10, but ultimately the result is same. Now to determine the after thresholding which value will be or which pixel will be lighting up, which will not, right? So what will be the condition? That any pixel which is greater than 120 will be lighting up and rest all the pixels will be switched off. This is the condition of this new thresholding value, right? So first element is or first cell is your 10, so it is much less than 120, so this will become switched off. Okay, now then this will remain switched on, switched off, off, off. All this will be off. Now you know why I changed that 110 to 10, because if I had kept it 110, then this particular pixel would have been switched. Switched on. So that would have created a problem in viewing, but that doesn't matter. But so ultimately, what we are getting this series of 7 pixels like this, which is light up. So this will be the shape of the dot, right? Now tell me one thing, that in the case of the first thresholding condition and the second thresholding condition, which dot size is larger? Of course, the second thresholding condition, the output that we are getting after the second thresholding condition, that dot size is larger, is it not? Now, if that dot size is larger, that means what? Greater amount of ink, greater area will be exposed in the plate by the CTP for this area, right? And greater amount of ink will be deposited, right? So this means what? When to choose the or how to choose this thresholding value will depend upon what type of image you are working with or what is the nature of the screen cell. Actually, I changed this. I should have shown you this second thresholding condition with another block of image, but I did not show it. I showed you with the same type of a screen cell. But the intention here is, see, when am I using 250 as a threshold? When I am using 120 as threshold? Tell me that. 250 means what? Highlight. 120 means what? Mid-tone. So naturally one thing is clear, that if in highlight area your dot size will be lower, but in mid-tone area your dot size will be larger in comparison to your shadow area, in comparison to your highlight area, sorry. So naturally your thresholding condition, that depends upon what is the nature of the image or nature of the area that you are choosing, or what is the nature of the screen cell to be perfect. Okay, so if it is a highlight area, then your thresholding condition will be higher to ensure that only small dots are created. But if it is a mid-tone area, shadow area, thresholding value will be lower, so that the overall dot size increases, greater amount of ink is deposited in that particular area. Okay, so hopefully, and so this is how we are creating dots and the entire concept. So previously, as I explained, all these things, how dots are created from the supercell, how this will be converted into a particular dot, which pixels will be lighting up. So this is how, that mathematically, this is how RIP engines work. This one very simple example, but nowadays it's very advanced. RIP engines are very advanced, much more advanced than this technology. But this is a very simple technique using which you can create dots out of a grid of pixels. Okay. I will try to show you some, because I don't have a RIP engine right now, ripping software right now. I will try to, I have, developed some very simple code to, implement this technique on an image to renderize it or halftone it basically. I will show you some example in Python. But before that, let me also show you, this is, so basically this is what? This is nothing but your aim screening. That for depending upon the nature of the area, your size of the dot is basically changing, right? So that is what the overall concept of aim screening is. The size, depending upon whether it is a highlight area or shadow area or a mid-tone area, the size of the dot will change. So that is what we have talked about. So this is ultimately your, you can say that, digital aim screening, right? Digital aim screening, where the size center to center distance remains the same and the size of the dot actually changes depending upon what. Now what I will talk about is a FM technique, digital FM technique. So there you will say very common technique. This is not really used in modern rips, but maybe some form or some implementation or some flavor of it is used. But what I will show you is a very generic type of frequency modulated screening, which is known as the Floyd-Steinberg error diffusion technique. It is one technique where you will see that the size of the dot remains the same, and ultimately the center to center distance, that basically changes, and that gives you a much more pleasing kind of a output, a visual appearance basically. Now in this technique, what I will show you is basically known as error diffusion technique. Now from the name itself, it is clear that error diffusion means, what does it actually mean? So whenever in the earlier example what we saw is that we are discretizing this entire image by thresholding it, right? But as soon as we do it, we incorporate some error into the pixel intensity values or the entire image, right? The basic fundamental or the basic idea behind this error diffusion technique is that we push the error slowly in small quantities to the next pixel, so that the overall error is reduced. This is the, basic fundamental of the error diffusion technique, and as a result of which you will notice that the dots are getting scattered in the sense that that is kind of a, FM. So let us say we are working with a 2 by 3 size image basically. Okay, so this is our image. We start from this particular point. Now what we do is we start from the existing pixel in consideration and we generate a for loop. So for the NP, that means number of pixel, what we need to do is we need to consider the present pixel and we need to quantize it. So how to quantize it? By application of a any thresholding function, for example. So let us say it is 128. So then we calculate the error. So what might be the error that has gone into this quantization process? So the error is basically the amount of value or the pixel intensity that was originally dedicated in that particular pixel minus the value which for the same pixel after it was quantized. Right, I will show you, I will give you some example where I will explain uh, how this can be actually done in real terms. So next, so this is how to calculate the error. Error means, again I am saying that, let us say that this is ixy, that is, let us say this is the original pixel intensity value for this particular uh, pixel, and we have first quantized it. Quantized it means we have thresholded it, that we have checked that, okay, is this value greater than 128? If yes or no, then that present value is bxy, and the error between the two after quantization and before quantization, that difference is the error. Okay, now next, this first pixel is done. Now next we move on to the next pixel, right? In the next pixel, so next pixel means this particular one, right? X and y plus 1. If this is xy, then this is x and y plus 1, right? Then what will be that kind of that value? That will be its own value plus 7/16 of your error. That means, why did I use this particular value of 7? I am using error part is all right. This is what the error is. Error, or that means the difference between pixel intensity before and after quantization, right? Quantization, isn't it? Now what I am doing is, I am pushing that error, I am adding that error, this part, I am adding that error to the pixel intensity value of the next pixel. Error was generated in this pixel. Now that error, that, not that error actually, that fraction of that error, 7/16 part of that error, I am adding to this particular pixel. Hopefully this part is clear. Now next, we are then going to the next pixel. So what will be the value of this particular pixel? This will also be some fraction of that previous error. This will be 3/16 part of that error. Okay, so similarly we can do this for the all the other pixels as well. So if we do this, so this is I actually, okay, so we can do this for the other pixels as well. So let us say x plus 1 and y, that means this pixel x plus 1 y is equal to I x plus 1 y plus, this will become 5/16 of an error. Okay, so that means what, I am pushing some fraction of error and I am adding that error to the next pixel. So next, after that pixel, the last pixel here is x plus 1 y plus 1, x plus 1 y plus 1 plus 1/16 of that error. Okay, so this, hopefully this part is clear. Basically all I am doing is I am finding out what is the error of quantization, what is the thresholding function, how did I quantize 128. In this case I have considered 128. 120 is somewhere in the middle, mid-tone. So after quantization, the error that is generated, error means the difference between original pixel intensity and the pixel intensity after quantization. So I will show you one example. So I am calculating that error first, and for all the upcoming pixels I am adding one fraction of that error to the next pixel. Okay, and once this is done, then finally we can close the loop here, right? Yeah, we can end the loop here. Now the question is, let us consider this particular example with a live example. Okay, so now let us take a look at one of the examples. So let me take an image like this, that is one image same intensity, same pixel intensity. This will make our problem much more easier. Okay, so now our thresholding value was what? Our thresholding value was 128, right? So first we start with this pixel. You can add, I mean, start from this also. This is a convention in most in many digital image processing books. That is why I'm using this. Okay, so you can start from here, no issues. So uh, first we will check whether 164 greater than 128. No, so that means this will turn to 0. So what will be the error? Error will be what is the original image minus after quantization, right? Original image minus quantization. So that will become how much? Original image was 64 minus after quantization it becomes 64, right? It becomes 0, therefore error is 64. Now what we do, we have to add fractions of this error to the upcoming pixels. That means 7/16. So this pixel will become 64 plus 7/16 of 64. That means this becomes 92. This will become, how much did we add? 5/16th, no? No, 3/16th. So this will become 64 plus 3/16th of 64. So I think this becomes 76, right? So this is 76. So similarly, for rest of the pixels also we can calculate and we will find out. So ultimately, after the first step, the image will look something like this. So this will become 0, this becomes 92, this becomes 76, this becomes 84, and how much will be this one? 116th. So 116th, 464, that means 68, right? So this is after the first step, after the first for loop is first time for loop is working. In the second iteration, what is going to happen? Again, this is done, this pixel is already done. Now we will consider this pixel. Now is this greater than 92 128? No, this is not greater than 120. That means this will become 0, right? So what is the error? Error again is equal to 92 minus 0, that is 92, right? So again we will add some fraction of this error to this pixel, this pixel, this pixel, similarly, right? So after adding the error, what will be the value? This will come up, the error value, I think 1/16th of that error value will come up to be 5 point, how much is it? 5 point, this 1/16th e by 16th value will become 5.75, right? Now when you add this, you go on adding this, all this value, fraction of this value with the remaining of the pixels. At one point of time you are running this for loop, and at one point in time you will find out that one pixel value, or maybe another pixel value, some of the pixel values will go above 128. Because what you are doing, why it will go above 120? Because you go on adding all these values, right? 76 plus 7/16th of 5.75, that will have some value. 84 plus 3/16th of 5.75, that will have a, so ultimately you are increasing the value. Remember, initially your original image was 64, so all 64. So now you see your all the pixels has become larger than 64, more than 64, and at one point in time there will be some values, there will be some pixel intensities which will go beyond the thresholding value, right? And at that point your loop will end. That means at one point, let us say that this pixel is going above, this pixel intensity value is going above 128 after a few iterations of the for loop. Then all these values would have become 0, but only this one would have become 1. That means your all these areas will be darkly lit up, I mean dark pixels will be turned off, and this pixel will be switched on. So this is how your uh, error diffusion, this is actually Floyd-Steinberg technique. So this error diffusion technique will work, and this will result in frequency modulated dots. So here you will see that for all the screens, screen cells, actually if you consider this to be a screen cell, again this is one screen cell. For this screen cell you can have multiple such dots which is lit up. That means the distance between the dots are uneven or random, but the size of the dot remains the same. What is the size of the dot? 1 pixel size, that will be lit up. So this is how you can create FM dots. Actually I will show you one example using one code that I have created to show you how this particular FM dot or aim dot digital halftoning technique can be applied to a particular image, and how RIP actually implements that. All these mathematical techniques, how RIP actually implements that.